So we have two functions, f of xy and g of xy. We have two functions. First function is function which we want to optimize. And when we're saying to optimize, that means find max min. Depending on the situation, sometimes you want to find max, sometimes you want to find min. And the over function is so-called constraint. So it's constraint. Restrictions, some extra conditions on the function on our x and y, and usually we will assume that our constraint equals to 0. That's how usually. One function has no restriction at all, f of x, y. And the over one will say g of x, y. There is some connection between x and y, and that should be equal to something. And we say we move it from one side and we'll say equal to 0. Okay. Then the following theorem is true, called Lagrange multipliers. So we have these two functions, f of xy and g of xy, and we'll assume that they are good enough. So let f of xy and g of xy be continuously differentiable. Okay. If point P y0 is a max or min of function f of xy subject to constraint g of xy equals to 0. So that's exactly the situation we have mentioned on top. So we have to function to maximize, in this case, or minimize, I put in parentheses, and we have constraint g of xy equals to 0. So we found it. Then at this point, what is happening? Gradient of function f at a point P and gradient of function g at a point P, they're going to be parallel. And here, assuming that gradient of g at point P is not equal to 0. Okay. So it's saying if function attains max or mean at a point, then gradient with respect to f and gradient with respect to g at the point, they should be parallel. Gradient f at p equals to lambda gradient of g. Okay. So let me try to maybe give you intuition on why that is true. And then I will write down a couple of examples how to use the Lagrange multipliers. We have g of x, y, our constraint equals to 0. So that is going to be like kind of curve. G of x, y. Then at this curve, we have at point P. Okay. Now what's going on at this point? Because gradient at point P of g is not equal to 0. At a point with coordinates x0, y0 is not equal to 0 vector. So what it tells you, it kind of tells you that you can find your approximation to a function at this point. So what it tells you that somehow you will be able to find maybe on that small interval around the point P approximation to function which gives you that g of xy equals to 0. So around, so at around point P with coordinates x0, y0, g of xy can be written as x is some function on t, y is some function on t. Okay. So maybe not on the whole interval, we can write down g of xy as a function on t, but in some neighborhood around here, we can write it as a function, as a parametric function. Okay. Real parametric function, because gradient is not equal to 0, so you can find your linear approximation, you can find your cubic approximation, anything, so eventually you can approximate the function. Okay, that's the deal. Now let's have a look at what's going on with our function f. So if I take function f, okay, and I look at points x and y, and because my points x and y should be coming from that curve, okay, so it should be x alpha of t, y. Okay, that's what actually my function is supposed to be. That's what's supposed to be near point P. Okay. Then I will take, now that's function on t only. It's called capital. And then I take its derivative, gradient of f, multiplying with derivative of alpha with respect to t, I guess, and beta with respect to t, right? Because you remember that's going to be derivative of f with respect to x plus partial derivative of x with respect to y and d beta dt. Okay. That's exactly what I put here. Okay. Now, so one more time. Okay. Now at P, point P, function has max or mean, its critical point, therefore the derivative of function f with respect to t, capital F. So thus f prime at point P is supposed to be equal to 0. So gradient f dot product with alpha prime, beta prime at P supposed to be equal to 0. Okay, that's the first observation. Second observation, if you look at the g of xy, which equals to 0, our constraint, I'll substitute alpha of t and beta of t into it, still equals to 0. We're still staying on the same constraint, so it's still true. Now I take derivative of both sides, left side general, so we're going to take gradient g times derivative of alpha, derivative of beta equals to 0. We're at point P. It's going to be equal to 0. Now, if I look at these two pieces of information, so let me maybe write it one more time on the next page. Gradient f times alpha prime beta prime at point P equals to 0, and gradient g times alpha prime beta prime at P equals to 0. That implies gradient f is perpendicular to alpha prime, beta prime. And gradient g is perpendicular to alpha prime, beta prime. So on xy plane. Now what is happening? You have alpha prime, beta prime vector. And you have gradient f, which is perpendicular to it. You have gradient g, which is perpendicular to it. If they are both perpendicular to it, therefore they're supposed to be parallel, and that, don't forget, that's a P. So that's exactly what Lagrange multiplier theorem is saying. If both are perpendicular to the third one, they were parallel. And that's exactly what Lagrange multiplier theorem is saying. So that's the intuition behind it.